Okay. Good morning, everybody. So let us start our lecture today. Today is November 2nd. Okay. So according to our syllabus, this week we will discuss heaps. So heap is another tree. Okay, a kind of self-balanced tree. Okay. It's not a BST, but it's a kind of BST. It's not actually, it's not a BST, it's kind of tree, okay? Self-balanced tree. We will discuss this. But before we start, do you have any question about test? About test 2? Do you have any question about test 2?
When might we get might our grades be posted on the D2L?
Yeah, you should see your grades in D2L.
Okay, I must have missed that. Sorry about that.
No, you should be able to see your grades in D2L. I publish all grades. Grades are published. You should see them in D2L.
Got it. Thank you.
Okay.
Will the test have a curve?
So carving, if needed, we will decide all the way before we make our final grade. Not for individually test carving.
Okay, thank you.
Anyone else has any other question?
Is there an answer key on D2?
Yeah, you can see your open your test and you can see answer.
Oh, okay. Thank
you. Okay. But I got 2-3 emails from some students. Okay. They disputed about some test question. Before we I open the test. Okay. But I will discuss this. Okay. So if I go to test and then the questions. As you see in the announcement, I clearly mentioned that there will be all questions will be from our slides, our lecture slides. Okay, some of you maybe try to answer this from outside resources and you got confusion. Okay. Okay. Let me open there. I got some email actually from 2 students actually. That is not from maybe your section, from other section. Okay. So let me spend a few minutes to discuss the questions that some student disputed. And let us discuss together whether I am correct or he or she was correct or you are correct. Okay. The first question as disputed is said that which of the following is not a stack application? So it says not a stack application. Okay. So then my answer key, it says concatenating two strings is the answer. What is that one? Question number 22. Question number 22. So this is in the slide. We have these stack applications. So do you see anything? It says that. Do you see anything? Is that it says concatenation up to string is the stack application. We never use stack to concatenate to string. Okay, so question number 22. Question number 22. Sorry, not this one. Okay, it says which of the following statement is not a stack application? So concatenating to string is not a stack operation. Stack is used for reversing a string, compiler design, checking a palindrome number, evaluating an arithmetic expressions. These all are mentioned. Mentioned in our slide. Evaluating arithmetic expression, checking palindromic string, evaluating postfix, okay, and reverse a string, but it does not say about concatenating two strings. Okay, so the next one. So the question seems to be correct. So has anyone any question about this? Do you have still any concern about this one? Okay, the next question was 23. How a stack can be implemented? Okay. Select all that apply. That was the question, right? How a stack can be implemented? Okay, using a linked list, using an array. We discussed these two in our lecture. Using a queue is not a way to implement a stack, although you can use using two queues. If you use two queues, then you can implement a stack, but that is a difficult implementation, and we did not discuss this in our class. Okay. So is everybody okay? The next question is number 28 and 29. Contradict this. Someone said 29 and contradict each other, especially since 21 asks for which are the valid QE operation and 29 asks for which are invalid QE operations. For both questions have the same answer, and all of them are listed correct. That is not correct. Let us see the question number 28 is like this. So question number 28. So question number 28. This is question number 28. It says which of the following are valid QE operation? Okay, so Q operation, we know that NQ and DQ, these are two valid Q operations, right? And it is the question, NQ and DQ are two valid Q operation. And question number 23, 29, it says which are invalid Q operations. So if we see over here, so valid NQ and DQ are valid. So push and pop are invalid Q operations. So push and pop, these are invalid Q operation. Okay. So if I even open question number 23, actually the same thing over here, I copied, which are invalid Q operation. Push and pop are valid stack operation, but not QE operation. Is everyone okay? Okay, then question number 31. It says which of the following are not QE application? Okay. So which of the following are not QE operation? Evaluating an arithmetic operation, arithmetic expression is a stack operation. Okay, at the beginning we see that stack, evaluating an arithmetic expression is a stack application, not a QE application. Okay, evaluating an arithmetic operation is not a QE application. QE application is palindromic string, palindromic number, either string or number, and printer QE. So if we go, even if you open our slide, okay, the student argued that as correct, although according to the lecture slide, for QEs, all of these are listed as QE application. Let us open the lecture slide. So QE application. So you see at the beginning it says stack Q operation in Q and DQ. Q operation. Okay, these are the QE application. Checking palindromic string or palindromic number. Same thing. Okay. Printer print QE, program input QE, and it does not say that arithmetic evaluating arithmetic expression is not a Q application. Okay, so this question seems to be correct. Does anyone has any concern about this one? Okay, the next one is question number 32. It says which of the following is are not appropriate QE application? Select all that apply. Okay. Checking a palindromic number was marked as correct on this question, but it is on the previous question marked as incorrect. So in the previous question, it was not marked as incorrect. Okay, the problem. Okay, so this student, I see that. I don't know. So this student, maybe he forgot about not. It's although in the test question I wrote it in all uppercase. So checking palindromic number was marked as correct because yes, it is not a. It is. It is a palindromic number or palindromic string is a valid QE application, right? So in that next question, I was asking which one are appropriate QE application. Here there is not. I think the student misleaded with this not. Okay, so here checking palindromic number is the QE application, and then simulation register checkout modeling application, that is a QE application, and checking breadth first graph traversal according to our slide. Breadth first graph application, graph traversal, and checking parentheses matching is application of stack, not for QE. Okay, so this question seems to be correct. Does anyone has any concern about this question? Okay, the number 34, it says how can a QE be implemented? Select all that apply. A QE be implemented using a stack or a linked list marked as okay. Using a linked list and using an array. We discussed this in our lecture, right? So how do we implement? So array implementation using an array implementation 1 using an array, and then implementation 2 using a linked list. Another implementation. Let me go. Another implementation. Linked list. Okay. So the question was how a queue can be implemented using a linked list and using an array. A queue cannot be implemented using a stack. So this question seems to be correct. Does anyone has any concern about this? Okay, the next question disputed as question number 41. In programming, everything can be done with recursion, can be alternatively done with looping statement. It is correct. But it vice versa is not correct. Okay, marked as the true as the right answer, although the contradicts something listed in the lecture slide. Every recursive function can be rewritten using loops. Yeah, that is here what is instead over here. Done can be done in programming. What we do, we write from program statement, right? So recursion is a function. So a recursive function also can be implemented using a loop. We discussed this. And then what is the reason that we use recursive method? Because we want to concise our code. Okay. Does anyone has any concern about this question? Okay. This student, another one, the question 46, a recursive method without a non-recursive, they made a typo over here, okay? It should be recursive. Part cause an infinite loop, yes. The lecture slide says a definition without a non-recursive part causes an infinite recursion. What is a recursion? Recursion is a looping, right? Whenever a function calls itself, that makes a loop. It calls itself again and again, right? Until we reach into its base case. So infinite recursion means infinite loop. So this question is correct. Does anyone has any question about this one? Okay. The last one is 49, number 49. The factorial of a positive number can be defined in terms of another factorial until the base case of factorial 0 is reached. Is correct. Because in order to write a factorial method, we can consider base case when you reach at factorial 1, that is 0, factorial 1 equal to 1, also factorial 0 equal to 1, right? So in our lecture, we discussed that. For factorial method, we can consider base case either factorial until factorial 0 or either factorial 1. So because factorial of 0 equal to factorial of 1. So this question is also correct. So this seems to me that all questions are correct. So I did not find any major mistake, any notable mistake that I need to give credit for any question. Does anyone have any other concern about any test question? How many of you are here? Why don't speak up?
I'm
No
here,
questions.
but I don't have any questions.
Okay, Sevi says no question, right?
Yes, no questions.
Okay. You know, it is for open book. For open book test, it is difficult to write test questions. I have to spend many hours to develop this test, to write this test. Okay, so it takes a long time to, because there are only 5 slides, right? 4 or 5 slides. English, stack, QE, and recursion. Only 4 slides. So if it would be a closed book test, then the question would be something different, like so that you can easily remember or something. It would be word by word, exactly same from our lecture slides. But since it is a little bit, since it is open-ended, open resources, so I had to make some questions, rewrite some questions so that you easily understand the fact, and then you can answer. Okay. That's it, but still, if you have any concern about any test questions, please let me know. Okay, and by this week, I will upload. Now let us go to our syllabus. Okay, so we have quiz 5. So this week, by this week, I will upload quiz 5, okay? Maybe tonight or tomorrow morning, I will upload quiz 5, and quiz 5 will be from trees mainly. Trees and BST. Also, it will cover heaps. Okay. Please make your plan to complete that quiz 5 by this weekend, and also assignment 6. Okay. So now let us start. Heap. So heap is a kind of balance, is a kind of tree. It is balanced tree. It is a balanced tree, okay? Or pretty balanced tree or nearly balanced tree. Okay, so as we discussed in our previous week's lecture, that binary search tree, for instance, a tree that has some criteria, right? There are some. One of the criteria of a BST is that its left child value is always less than the root value, and the right child value is always greater than the root value. And there is no duplicate values in a binary search tree, right? And then in our previous lecture, we discussed what is a tree, what is in general a tree can have 0 or more child nodes, but a BST can have only 2 children nodes, 2 child nodes. Okay, binary tree can have only 2 childs. Okay, and then we discuss full binary tree. That means every non-leaf node has 2 child nodes. And complete binary tree, the tree is filled top to down and left to right. Is complete binary tree. Okay, I will bring up an example today also, and then BST, and then we will today there's sometime BST binary search tree are become imbalanced. Okay, so in that case, it is better to get balanced tree. Balanced tree. Okay, so what do you mean by imbalanced? So what is meant by imbalance? Give me 1 second, please. So if we have a data set like 10, 8, 12, 6, 14, 4, 16, 22, for instance, like this, okay? Then first of all, we will put 10 over here, right? And then 8 less than 10. We are drawing a BST. So it goes left side, and 12 is greater than 10, will go right side. 6 is less than 8, it will go left side. 14 is greater than 12, it will go right side. Okay, it's 14. Okay, and then 4 is less than 6, it will go left side. And 16 is greater than 14, it will go 16. 20, it will go right side, right? 2 is less than 4, it will go this side. And now if I counter 5, okay, and then 7, maybe 15, okay, maybe 11. How does BST will grow? So 5 will go. 5 is left side of 10, so left side of 8, left side of 6, so left side of 6, so and also right side of 4, 5 will go over here. Okay, and the 7 is right side of 6, so 7 will go over here. And then 15 will come ultimately over here. 11 will come here. Okay. So this is a BST. Okay, so for the data set, for our given data set in this order, we got this BST. So now, can anyone please tell me what is the height of this tree, of this BST?
5.
1, 2, 3, 4. 1, 2, 3, 4. I see 4.
Copy.
Got it? That's okay. Now, instead of given this data set like this way, if this data set is given in an ascending order, for instance here, like 2, 4, 6, 2, 4, 5, 6, 7, 8, 10, 12, 14, 10, 11, 11, right? 11, 12, 11, 12, 5, 6. Okay. 14, 15, 16, and like this way. So then how this BST will be growing? Then 2, and then 4 is greater than 2 will go right side, and then 5 will go right side, and then 6 will go right side, and 7 will go right side, and then 8 will go right side, and 10 will go right side, 11 will go right side, and then 12 will go right side, 15 will go right side. You see that this tree is growing linearly. Growing. Grown BST. So the height of this tree will be 1, 2, 3, 4, 5, maybe n minus 1. Height will be n minus 1. Right? So it is the number of given data. So in this case, if we want, in the worst case, because our intention was not worst, our intention was not bad, but we got a data set in an ascending order. Okay. Similarly, it may happen if you get data set in descending order. So for a sorted data set, that is our expectation. For many cases, we expect sorted data value. But a BST grows unexpectedly linear time. So the time complexity will be big O n. That means if we want to check whether a value, for instance, 16 is available in this list or not, we need to start from the root and then go wall by wall in, one by one after. So we may need to check all the elements. Or in the worst case, if the value does not exist, still we need to go all the way in. Okay, so this is sometimes inefficient. Otherwise, for instance, if you had a balanced like this BST, then it would take, for instance, for this one, if we have 10 data set, then we need to do 10 looping or 10 searches. But over here, we need to do only 3 looping, 3 searches, because its height is 4 and its height is about 10, n minus 1. And here size will be log n, LZ n, height. For a balanced tree, height will be LZN, log n. LZ means log with base 2. Okay, so this is a problem for a BST, that it is sometimes it may grow unexpectedly linearly. So in order to resolve this kind of issue, we expect for other kind of trees, okay, that are called balanced trees. They are called balanced trees. So a heap is a balanced tree. Okay. So heap is a complete balanced tree, and it has criteria that for a heap, its parent node is always greater than its both child nodes. Okay, but unlike a BST, heap is different, because in a BST, all root value is greater than left child value, but less than right child value. But here, this parent or root is always greater than both child values. And then now let us come with some examples. In that way, binary tree will be nearly balanced. Nearly balanced, that means the height of the left child, height of the left tree, not left child actually, height of the left subtree minus height of the right child tree is taking absolute. That means the difference between the height of the left subtree and right subtree is less or equal to 1. Okay, so a heap is a nearly balanced binary tree, or we call it a pretty balanced binary tree. Okay, but a heap is not a BST. Why is a heap is not a BST? What is the main reason that a heap is not a BST? Can anyone please tell me? Who can tell me what is the main reason that a heap is not a BST?
Because BST is ordered and a heap is not.
What do you mean by order? Can you please tell me your answer in other way so that it becomes clear? That is the main reason. You see that? In a BST, left value is less than root and right value is greater than root. But in a heap, root means parent is always greater than all both sides. These two values this contradicts. Okay. So now let us see some examples. Okay. So here in a heap, the main property is that heap is a complete tree. Okay. What is meant by complete tree? Complete tree. Okay, let us see that don't forget that, don't consider the values. Okay. For now, consider only the tree format. Okay, tree and node format. So which one is a complete? Which one or which are here complete tree? And which one is not a complete tree? Can anyone please tell me? How about the first one? Is it a complete tree? Is it a complete tree?
I think it is.
Okay. Okay, the first one is not a complete tree. Thank you. So in order to be a complete tree, for instance, the tree structures need to be like this. So here, for instance, even for a BST, so we need two nodes, right? We know that each has two. Okay, and then like this. Okay, so here this is not a complete tree. In order to be a complete tree, for instance, you have to complete the nodes from left to right. All leaf nodes needs to be completed from left to right. So before you complete these two, you cannot go to here. You cannot, even before you cannot go to this level. Okay, before you complete this level. So here we have completed this level, right? So here now, so one, let me spell this one is a two children. This is correct. And then this one has two children, then is correct. This one has two children, that it is correct. And this one has one children, and this one has two children. This is correct. Now, if I have one more node to add in, I cannot add over here. I cannot add over here. First of all, I need to give priority to this one, and then this one. Then I need to give priority here, this one. Then this one, after that this one, after that one. So the tree needs to be grow from up to down and left to right. Then it will be a so here you see that this one is not a complete tree. This is not a complete tree. The left side. The right side also is not a complete tree. Okay, so here, so this one is not a complete tree. Delete this because the 11 should come over here. Okay, this is missing, so if we cannot keep this missing. So it is not a complete tree. This is a complete tree, and this is also a complete tree. Now, in order to be a heap is a binary tree that meets the following condition. So heap is a binary tree, not a binary search tree. Remember that. So the nodes key, each node's key is greater than the its children value. So let us check that. 97, 91 is greater than 77 is good. Greater than 47 is good. But is greater than 77 is greater than 69. It is good. And 3 is greater. 77 is greater than 3. It is good. And 48, 46 is greater than 11. It is good. But in terms of this, it satisfies this condition, but it does not satisfy this condition. So it is not a heap. Now let us see this one. So it is a complete tree. So it satisfies this one, and also it satisfies, you see that, this condition. So it is a heap. Now let us see this one. So 52 is not greater than 72, so it does not satisfy this. It does not satisfy this, but it satisfies this. Okay, it satisfies this. So only the middle one, it satisfies both conditions. So this is the middle one is a heap. Okay, but other two are not heap. Does anyone has any question? So the criteria, the first criteria, okay, to ensure the first criteria, we use an algorithm to make sure that all parent node value are greater than the children values. It's called Heapify. The process is called Heapify. There is a algorithm. It's called Heapify algorithm. Okay, it's called. There are two kinds of Heapify algorithm. It's called Heapify up or Heapify down. Okay, upward Heapify. If you find going through up, or if you find going through down. So in case of inserting an element, we use upward heapification or reheapification, or do we say? So for instance, in order to add a node in a heap, we first try to make it a complete tree, binary tree. So this is the element, we will come over here, like 42 will come here. Then now we will check whether it satisfies the other condition. What is the other condition? That all parent value will be greater than its child value, corresponding child value. So 42 is not greater than 27. So this needs to be swapped. So 42 and 27 are swapped. Now we will check 42 against its parent. 35, right? 35 is less than 42, so 35 and 42 will be swapped now. So 42 will come over here, and 35 will go over here. Now you see that this one is correct. This 35 is greater than 27, and 35 is greater than 19, and also 42 is greater than 35, and 42 is greater than 21. Then now it will check 42 and 45, right? So 45 is greater than 42, so nothing to do. Okay, then this is done. So the process is called up word heapify. Heapifying, that ensuring that it maintains a heap. Okay, it maintains the property of heap, that a value property that every child node is less than its parent node. Okay, so in order to do this, for insertion, adding a node, we do heapify, upward heapify, and then, for instance, okay, now in case we want to remove the top of a heap, remove some element. If you want to remove some element, okay, so what do you do? For instance, if you want to remove 27, then it's easy to remove 27, right? The last element. Okay, now if we want to remove other elements, then that is a little bit difficult. For instance, if we want to remove the root 45, okay. So what do we want to do? We need to move the last element. Last element is 27, and put in on 24 over here. Okay, move the last element on the top of the root, so then 45 will be overwritten by 27. Now apply downward reification process. Move out of the place to move downward, swapping with the larger child node with the so let me show you what we do. Now we need to download. For instance, now what do we need to do? We need to move this one, right? Because this is not in position. Okay, then what do you need to do? We can, what is the greater value? 27, because it's the children 42 and 23. Which one is greater? So 42 put in the place of 27. Okay, then 27 will come over here. 27 will come over here, 42 will go there. And redo this. Now compare 42, 27 with 35 and 21. So 35 is greater than 27, so swap these two. Okay. Now we have 19 and 27. 27 is greater than 19, so this is in place, right? We have to do nothing. This is done. Okay, in this way, we can remove a node from a heap. The process is called heapify. Heapification. So we'll come up that algorithm, okay? Maybe not today, maybe in our next lecture. We have another lecture. So okay, how to implement a heap? Let us do this today. So there are like how we implement a linked list, stack, and queue, right? So we can use an array of data. We can use an array, okay, to implement a heap. So here 42 will be root, and then we saw a formula, right, in our previous lecture. How to find the left child for a node, and how to find the right child index, right? So left child index will be 1, and 35 will go 1, and the 23 will be 2, and then after 35, 27, 21. You can review that. What is the formula? Let me get that one. Okay, we have a formula for this one. That one linked list. What is that one? Let me see the formula. Is on the BST, right? Okay. So here. So left child for any node in position I. So left child will be in position 2i plus 1, and right child will be positioned in 2i plus 2. Okay, so for I start from 1. Okay, so for I, okay, always store root is always put in index. Okay, so now okay. Okay, so the formula will be left child index equal to 2i plus 1. So here for I equal to 1, I equal to 1, even I equal to put 0, then 2i, that will be 2 times 0, then plus 1, that will be 1. This will be left child of with index 0. Okay, so this is root. Root will be index 0. Okay, and the right side index equal to 2i plus 2. So right child index will be 2i plus 2. And then for root, this has index 0, right? This is index 0. 0 plus 2 times 0, that means 0 plus 2. This is the 2 is the index of right child of 0. Right side of elements 0. So for this element 1, okay. So who will be left side? Left side will be position will be 2i plus 1. So I equal to 1 over here. So then 2 times 1, 2 plus 1, 3. So at position 3, that we will get 27. And then for this one, what will be the position of right child? So right child will position will be 2i plus 2. So this index is I equal to 1. 2 times 1 equal to 2 plus 2 equal to 4. That 4 will be right child. Okay. So the left child index is 2i plus 1 and right child index will be 2i plus 2. This is a quiz question. Okay. So in this way, we can implement a heap using an array. And definitely we'll need an algorithm to ensure the properties of max heapify properties. That means the root values is greater than the child values. We use an algorithm that is called max heapify. Okay. So there are other trees of BST, B plus tree that we are not discussing for this course. Algorithm is not discussing in this course. So that is out of index, out of coverage of this course. So there are other trees like AVL tree, red black trees. Okay, so that maybe there is a list in the front. Okay, split tree. These are the trees that you may know this in your data algorithm analysis course or advanced data structure course, not in this course. Okay, so that's all for today, and then in our next lecture we can we may discuss something more about the implementation of a heap. Okay, and let me see what the book has. The book. So 11 is balanced tree. It does not say heap. Okay, heap. Okay, heaps is balanced tree. Let me see. Priority key and heap algorithm. BST. B tree. We are not discussing B tree. Okay, so I think there's another book that is better. This is better heapify algorithm. Biochemistry. Heap. Okay. Heap is used for heap sort algorithm. That is okay. It's max heapify algorithm. So this is the max heapify algorithm. So maybe in our next lecture we'll discuss. This is the small algorithm. The process that we discuss, how do we swap 11 from one position to another position. Okay, we'll discuss this So this is MaxCPP algorithm. It maintains the heap property. Yeah. So let me give please give me a few minutes that I to take attendance. Okay, today is October 28 October was the test 2. Today we do not take attendance, and this is 2 November. Okay. Please respond to my attendance call. And Jason,
Here.
Matthew, Daniel, Myers,
Here.
Antonio,
Here.
Jamie, Treton, Alisa,
Here.
Taylor, Ernest, Angel, Jidan,
Here.
Cody, Isaiah, Jimmy,
Here.
Isaiah's here.
Savvy,
Here.
Loyal, Dave,
Here.
Karen, Mikhail,
I'm here and Lau's here, just in chat.
who is also here?
Lau, Lucky, Ruki,
Okay,
number 18.
okay.
Tyler Crawford is also here.
Thank you. Jack, James, Brandon.
Here.
James, Brandon is here.
Brandon is here.
Noah, Alan, Kenya.
Here.
Who?
Kenya.
Thank you.
Zach
Jimmy,
is here.
Jimmy's there.
Jack is here.
Yes.
Jimmy is here. Lilibia,
Here.
Jesus, Cameron, Sebastian,
Here.
Alex,
I'm here.
Justin, Daniel, Andrew.
Here.
Nicholas,
Here. Here.
Jessica, oh sorry, I forgot to stop recording.